All right. So let's go to our bag of words file notebook actually. So let's do a bag of words and first start with explaining how it works. So our example is a binary classification, and it is essentially it's a sentiment analysis, positive or negative sentiment. Let's see how bag of words approach work. Essentially, in this technique, we will break down each text into tokens, and normally tokens are words, but it could be not just single words. It could be 2 words or 3 words back to back or more, or it could be characters. Instead of word engrams, you might have character engrams, and like 3 characters back to back or 4 characters back to back. But for the sake of simplicity here in this example, let's keep it just as a single word. And we take those tokens, we break down the text into those tokens, and then those are our features. And remember, we can't work with strings as a feature in our model, so we need to map them into numbers. So, and we use the one-hot encoding that we had in our previous tutorials to do that mapping. And then at the end, the document would be represented by the sum of those words corresponding to each token in that document. So for instance, imagine the corpus. The corpus is the set of all documents that you have. Your corpus has these 2 documents only, and then you would have only these words as your feature. Dog is playing, I love my. Dog is repeated there. So these are your features, and then you do one-hot encoding. Now dog is mapped into this vector, and then is playing, and so on. Just remember, we had other versions of one-hot encoding. In the other version that we saw before, we had, instead of like this 6, for these 6 features, we mapped them into 5 values, because the other one was induced by the other 5. But in here, because we are going to do some other normalization, normally in this vector, we keep all the 6, and so this space has like 6, length 6, or dimension 6, which is equal to the number of features that we saw in the corpus. Now each document is represented by the sum of those vectors. So first document is represented by this, and then this is the second document. We have some normalization techniques that we normally apply before jumping to the modeling, because these are the features. So this is the feature vector for the first document. This is the feature vector. Now this is structured. Now we can work with models and train models, and make predictions and stuff. So but normally we do some other pre-processing on top of these. One is term frequency, which is essentially giving higher weights to terms that are more frequently appearing in a document, in a single document. Or term frequency, inverse document frequency, which means that you do the term frequency and also you do inverse document frequency. Inverse document frequency is a coefficient calculated based on the whole corpus. Sometimes some tokens like the THE is appearing many times in a document, so that kind of doesn't give any much information. So you might want to remove or downgrade their importance in that vector. So in that, when you have IDF activated, it will downplay those as well based on the whole corpus. We have lemmatization, stemming, that also, like, these are conventional techniques that you could use to kind of avoid exploding feature size, because if your corpus is big enough, it could have millions of words in it. So this is one way to keep the dimension low. But we will see. We won't use this. We won't use this in our examples here. Or lowercase. Lowercase is another one. We are gonna try it. So these are all for reducing the space dimension here. Here it's 6 is small example, but it could be like 60,000 or more, which is still okay. So let's go to our example. All right. I'm using Pandas data frames, and the data is coming from Kaggle. This is the link to that data. I have already downloaded. There are multiple files. Let me see. Actually, I might. So these are the files. I have an extra one here. Just ignore that. It's my own. But normally each one, like Amazon reviews, IMDb reviews, and Yelp reviews, they're already labeled and in two formats, CSV or text. I'm using the text format and reading them into tables. These are Pandas data frames, which are similar to Spark data frames, if you remember. You can take a look at the first few rows and check like this. Wow, love displays sentiment is 1, which is positive sentiment, and crust is not good. This is a negative sentiment. Could check the size. I'm concatenating all these data frames on top of each other, and we have about 2,700 rows all labeled. I'm checking the distribution of the labels. This is a good practice always to do some EAD, exploratory data analysis, before you jump into modeling. You could see that the balance is it is balanced. 0 and 1 sentiments are appearing almost the same number of times. So this means that like some metrics like AUC/RRC is safe to use. So essentially, sometimes you have to be careful about the metrics that you're using. It could be that your class imbalance might make metric very optimistic, and so you might be misleaded. I am making a small example here to illustrate some of these concepts here. So this is a small data frame I created. Remember transformer, estimator, and pipelines from the first two set of tutorials in Spark. They're the same here in Python as well. So I'm not gonna review. Like, feel free to go back to tutorial 1 to check the details. So we are going to use count Vectorizer, which is essentially gonna create these actually I should say these vectors based on counts. So like dog is appearing 1, so you will have 1. Something like I is not appearing, so it will have 0. But also it has some additional arguments that it could make it a little bit different. Tf-Idf Transformer. This is named Transformer, but essentially the one that we are using, since IDF is set to true, it is an estimator, and it fits on the data set, and then it becomes a transformer. Logistic regression, you all know about that, and pipeline. Double question mark and the object name or function name makes it easy for you guys to dive into the details and see like the arguments. What are the arguments for this function, for instance? What are the default values? Description about this function, what it does, parameters are explained pretty good most of the time, so make sure you use that. I'm gonna actually go over some of them, like analyzer. Remember I said the tokens could be either words or characters, like word engrams or character engrams. Here you will set them here. You could also set the engram range. If it's words, how many words, like 1 or 2, or both word engrams of 1 or 2. Like if you want both engrams, 1 engrams and 2 engrams, you have to set this here 1, and this should be 2. Stub words. Stub words are the words that have that appear a lot in text, but they don't have any specific meaning, like the the I mentioned, de or a or an. So it has a default English stub words list, but you could pass your own, or you might say just don't use anything. Lowercase, by default it will lowercase your text before tokenization. and many other or maximum number of features that you want to have in your model. So feel free to check the details for each of these. So I am moving forward now. Count Vectorizer. Let's start with this. It has a bunch of input arguments. I'm setting just a few of them. Binary means that whether you want to count all the occurrences of one word, or you want to just either say this word appeared in that document or not. We'll see in the example below. Star Wars, this is the default one, English Star Wars, that already is there, and we will use it. Engrams, so we will just look at the one words as tokens. We will fit it on the small data we defined above, and then we transform that. So this is the small data, the small sample that we had, and then after you make the transformation, it looks like this. Each document now is a vector, and case and good and money appear in the first document, so their values are 1 and the rest are 0. Some of you might not know exact, so if you, let's say you want to check this small transfer just by typing that object name, you might not find it easy to read that because it's a sparse matrix. So this is the way I normally go about it. I check the type and see this is sparse matrix, and then I'll Google it and find the best approach to look into that object. And .a is the best function to call, and it will make it very readable. Tf-Idf, as I said, we are using the IDF part as well, so I set it to true. So it's now an estimator, so we fit it on the small data that we have transformed, and then make the transformation. And now you can see that that values 1 are now changed based on term frequency. Term frequency is computed based on the document itself, as well as inverse document frequency, and inverse document frequency coefficients are computed based on the whole corpus. Well, one thing I forgot to mention is that in here, since we set binary to true, this good is 1. In this third document here, we have good product, really good, love it. Actually, good appears twice, but if we set that to false, if we set this binary to false, then this value should be 2 because it appears 2 times. So logistic regression is like before, just the penalties like before L1 or L2 or elasticnet, and the C is the inverse of the regularization parameter. Random state, I set it to 21. It's a good practice always to, if there is this option to do that, because normally when you change the other parameters, if there is this randomness under the hood, you want to make sure that randomness is fixed so that you could see what is the impact of changing those parameters, rather than sometimes if you don't do that, automatically you might get a different value because of that randomness thing, not because of changing the parameters. Text classifier is the pipeline that has the count vectorizer, and then after that we do a Tf-Idf, and then we have our classifier. I put this SGD classifier as well here because this is kind of a generalization. This has many different classifiers in it. By default, it's the SVM. SVM. Some people like SVM for text classification. I personally I like it, but for some metrics I encountered some bugs, so I kind of caution you about this. So make sure that if you use it, you use the version that doesn't have that bug. In here I am doing the train test split. 35% are going to the test set that we set aside. Again, I'm setting a random state. Now I fit that pipeline into the training portion. Before getting to that model, I need to do something. That thing is here. If you look at the test portion, the sentiment, the sentences, and the sentiment, you see that the indices here are kind of the original indices. So because we randomly selected these, the first four are this. They're not consecutive. They're not starting from 0, which is fine, but because we are gonna later use some other functions, we need to reset them. So for doing that, I check what is the type of this, how I can Google it. I'll see, okay, reset index is the one I should use. I'll do that, and then there's this option that you can say drop the original. Otherwise, it will just add the new indices. But you say, okay, drop the original one. It will drop that, and you will see that now those series are the indices are starting from 0 and so on, and everything is good to go. I'm doing some lookup here. I want to see how the prediction goes. In general, this is a part of good machine learning practice. You want to check your model against some of the test or validation data. I am checking, like this sentence, the original, predicted label is 1, which is correct. The atmosphere is modern and hip while maintaining a touch of coziness. This is positive. And this is the probability that is predicted. It is on the boundary. It's not the best. I mean, I would have expected this be larger, and this is the original label as well. So this is somehow saying that, hey, your model is not that good. You might want to check other ones. I'm sure there are some mistakes, like this is predicted 0, but it's actually 1. And here I am first using that model that I fed to predict on the training data and then predict on the test data. And then I'm using the metric object to do some report of some metrics like precision, recall, F1 score, and then confusion metrics for each of them. This is for the training data, and this is for test data. You see the precision is pretty good in the training data, recall as well. And also this is the confusion metrics. I strongly suggest you to have this confusion metrics always computed and check the numbers. Many times, so as you know, this is the rows are the actual labels. So this is label 0, the label 1, the true labels, and the columns are the predicted. So column 0 is the predicted label 0 and predicted label 1. So this means that it was actually 0 and we predicted it's 0. And these are like 892 examples. We're actually having label 1 and we predicted label 1 for them. And apparently this is the false negative and this is a false positive. In many cases, at some point, up to some point, you could optimize these values, like reduce this and this both at the same time. But at some point, there is a trade-off. If you want to make this go lower, this might go high, or this. If you want to optimize this might not change in the direction you want. So there you need to see what is your. Is it a medical text classification? Do you want to have you want to make sure that you have the lowest false positive or lowest false negative? That's where you need to check your use case. So this is the values we get from that train model for the test portion. As you see, the precision has dropped dramatically to 80%. This is where we can see definitely this is overfitting, and also the confusion metrics is not as good as this one. This is definitely showing overfitting, and this was expected given the size. 2700 label rows is not that many. Almost any model you train, you will have this issue with. But this is the reality in many companies, many startups, many mid-sized companies. They don't have that many labeled training data. So keep in mind, you might want to start from this low size training set, and then later you might get more and more data as you go. Metrics has different, this metrics here that we're using has different other functions. Feel free to jump into them and look at them. Also, I'm assuming that you guys know about micro versus macro or weighted averages for all of these, recall or precision. Just remember, sometimes these values are the same. It's not a bug or something. You might want to search that, or you might want to write it down, and you will prove it. Hey, okay, this is expected. Like in multi-class classification, as I mentioned here, macro, average, precision, and recall are always the same. Essentially, these two numbers are the same, and this is expected. I'm trying our train model on one sample just to see dogs love us. This is 72% positive, which is expected. This is good. 1 week later, this is not a joke, this is reality, and 1 week is just a good estimate. Essentially, you have to do many iterations until you reach a point that you say, hey, this is not good enough for our production level. I'm skipping that later, I'll get to that. So after 1 week, I realized that I need to use word engrams. I don't want to use stop words, word engrams. I want to use both 1 and 2 engrams. Maximum features are 1 is 2000 and binary is false. And then the rest of that, I'll train that on all data now instead of just the training portion. And now I can make it portable by using Pickle. Pickle will serialize your model to disk, and then later you can load the model and make predictions with that loaded model. So during that 1 week, so before getting to that 1 week, let me just show you this engram here. So you see engram, instead of like discount vectorizer, if I use discount vectorizer, let's say engram, okay, this is 2. You see all consecutive word tokens are appearing here. Consecutive words, I should say, would be a token, like good case, case money. So these stop words are removed. Case money, good case, and so on. Good love. Or I could say 1, 2. So you have case money, good case, and so on. Or I could, in this one, if I don't remove stop words, oops, sorry, let me see what happened. Oh, sorry, this has to be none. Now, if I don't use any stop word, all of them do not, for the, love it, not waste, well, not, should not be a stop word. I would say the money, these are going to be included as well. So yeah, I will clean it later for you guys when I upload this file. Okay, during that 1 week, this is just one example of what you would do. You could do many other things like cross-validation and stuff like this. I am doing a grid search on the parameters that I could pass to these estimators. And essentially, one thing I'm doing is that I take two metrics like precision on trained data and precision on test data and take the ratio. And if the ratio is above something or within a boundary, and the precision train is above some threshold, I will mark it somehow to kind of notify myself. So after that, after I run the grid search, I'll get all these results, but these ones are the ones that kind of are good to check. And after running it, I noticed that like this is giving me precision train 0.79, precision test 0.78, and I'm gonna use these parameters in that excuse me, in that text classifier that I fit on all data. So essentially I'm getting about 80% precision, 79% precision. But note that since our data was very small, you could expect that we are always overfitting. And in the next video, I am going over the next technique, which is embedding, solving the same problem with embedding.